Okay, lecture number 20. Um, okay, so for review, on lecture 18, we went over the analog to digital converters for like a dual ramp right here, where it's based on the times going up and down the ramp. For delta sigma, we also looked at the analog digital converter for that as well. It's based on an integrator, this n-bit DAC that goes and feeds that back for the negative feedback. Also, we looked at sample and hold methods for capturing your front-end data so it doesn't change prior to you actually analyzing it. And also, we started looking at oscillators and looked at the Barkhausen criteria for oscillation. Then for 19, we looked at sinusoidal, which is based on positive feedback. And then we found out that for sinusoidal, this down here, the denominator of your amplifier of your whole system, it needs to be 0. So that means that your loop gain needs to be 1. And also you have this criteria that needs to be 1, and also the phase of that needs to be 0 or 360. We looked at two types of oscillators, the Wien-Bridge oscillator and also the phase shift. So the Wien-Bridge is like this. Here's the feedback loop right there. We extended that out, and then we looked at the loop gain for that, and that's the output, that's the input of this loop right here. And then we found out what that was. Then once we have that, then we can apply the Barkhausen criteria to determine what these values need to be in order for the gain to be 1 and the phase to be 0 or 360. For the phase shift, we actually did want it to be 360. So what you do here is just add up a few things and just make sure all your phases add up to 360, which is the same thing as 0 degrees phase. We looked at this type, and we looked at the loop gain again. We did nodal analysis, and we also did this inverting op-amp right here for that. And then we did the Barkhausen criteria for oscillations. Okay, so, oh yeah, and we also did some nodal analysis stuff just to make sure, to remind everybody how that type of thing works. And so remember for that, what you do is for every node you have, you're going to have, let's say this is a node you're interested in. Let's call that node 3. Here's node 1, 2, 4, 6, and let's say that's 7. And then for each one, you have some type of impedance. It could be a combination of resistors, capacitors, inductors. And it can have other nodes, right? But for when you're doing your matrix analysis, for your for the matrix that's at 3, 3, so 1, 2, 3, 4 on that way, then 1, 2, 3, 4 on that way. At 3, 3 right here, this is the location where you add up all of these. So if that's 1, 2, 3, 4, you sum up all of your impedances, and it all goes into that slot, okay? And then you just have to worry about the cross terms, and those are the minuses of each one singly. So for this one, for 4, you're going to have minus Z4. For 2, you're going to have, there's 2 of them. So if this cross one at 3, 4, and also 4, 3, so Z4. At 2, you're going to have, let's call it, did I run out of numbers? Okay, make that 5 then. Okay, so at 3, 2, you have minus Z5, and then minus Z5. Well, I have a 6, but let's do a 1 right here. You're going to have a minus Z1 and a minus Z1. So those are your cross terms, right? And if one of these happen to be a voltage source, for example, like this, where that V2 was that voltage source, then on this side over here, try to get a better marker. here's all your voltages. And here's all your current sources over here. So then for that one right there, let's put two of them. Okay, so say that one's also source 2. So over here you would have Z1 V1 plus that one right there, Z5 V2. And those would be your current sources for this row. 1, 2, 3, 4, on like that. If there's no sources, you just put a 0 there. So for no current sources going into that node. And that's just for that node. And then after you get done with that, you do that for the other ones. But most of the time, well, a lot of times it's going to be really simple like this. And if we did that one right there, you would see that it's just like KCL. So if we did the top row, that's oh wait, I'm sorry. These right here are conductances, not impedances. So everything is 1 over. Sorry about that. Okay. So for that one, you have your SCV 0 prime, and that equals to V1 times 2 SCs plus some conductance there, and then minus the SCV2. Right? And then if we were to try to put it in the form of what we're used to looking at, what we would say is it's going to be V1 minus V0 over okay, then plus V1 over, minus V2 over 1 over SC plus V1 over R equals 0. It'll look like that for one of the KCLs for that particular node. Okay, and that's like that node right there. So we have this one, which is that voltage minus that voltage over this right here. Then it's this voltage minus that voltage over that, which is right here. And then this voltage minus 0 over that, which is right there. And so that's just to validate for you guys that this is, KCL. Okay. Okay, so continuing on, we're going to look at nonlinear applications in a circuit using positive feedback. Okay, so let's quickly go over the diode, the IV characteristic of a diode. So here's a diode right here, anode, cathode, and here's the conventional current flow right here. And if current is flowing that direction, you have forward bias. Here's the IV characteristic. So here's the voltage right here across that diode, and here's the current right here. And so here's some characteristic things that you may remember. There's this knee here where it starts turning on, and for germanium type it's like 0.3 volts. For silicon type it's 0.7. Okay, and this is when it's forward biased. That means current is flowing this direction when this voltage is higher than that voltage. Now when this voltage is negative right here, when this voltage over here is higher than that voltage, what happens is that you have very little current flow going that direction. So current is going this direction, but it's very small. It's like 50 milliamps for germanium, and minus negative 20 milliamps for silicon. But then if that voltage over here gets high enough, then you'll have this breakdown of the material, and then current just flow through, okay, at some breakdown voltage. Okay, so that's quick overview of diodes. Okay, and the reason we need that is because we're going to talk about some things that actually use diodes. Okay, so this right here is called a precision half-wave rectifier. And what's really nice about this is that this right here is the voltage transfer characteristic. So it's actually much more precise than something like this if you just have that alone. First of all, as you can see here, it looks like the voltage is starting off right here. And over here, there's sort of like this voltage that has to get through first before it turns on. Okay, and you don't have that problem here. And yes, I know that this is like voltage and output voltage, and this is output current right here, but you get the idea. Okay, and also it's pretty much zero over here for the output right here if it tries to be reverse bias. Okay, so by combining an op-amp and a diode, you can make something called a super diode, which is this precision half-wave rectifier. So the output V0 is a rectified replica of the input signal Vi over here without loss of the diode's voltage drop that I was just talking about. So it just starts taking off. So the IAMP forces the voltage across its input terminals to be 0. Okay, that's what's happening here. And so for a voltage that's greater than 0, if this Vi is greater than 0, then the output voltage equals Vi. That voltage right here equals that. And the current is actually positive. So this current is actually passing through this way. And of course, the current is not coming from here because this is considered to be like an ideal op-amp. So no current flow here. So this current going this direction is coming out of the nose of the op-amp and going straight through. Okay. Okay, so let's talk about how that works. Okay, so for this, for Vout being negative, the currents try to be negative, like this current right here tries to go this direction. It can't go this direction, and really because of the way the diode works, it doesn't want to go. It's really difficult to go that direction too. Okay, so what happens is that the diode cuts off, this current is 0, and the feedback loop around here is inactive at that point. And then so what happens is that the output voltage becomes 0 because the current is 0. So if you have 0 current, if this current is 0, then there's no voltage drop across this resistor. So the voltage here is the same as the voltage here, which is ground. So for positive voltage over here, then this output voltage is just Vi. For a negative voltage here, then the output voltage is 0, and that's how you're able to get this nice output right here of the super diode. Okay. Oh, and another thing, so what happens to this voltage drop here? So let's call this voltage drop Vd across here. So what happens is that the voltage at V1 right here, it accommodates both of these. So you can take this voltage to be Vout plus that voltage at this point. And then as you're going across here of a drop of Vd, then that voltage right here will be this voltage minus Vd, which is just Vout. So that Vd is being absorbed into that V1. Okay. All right, so there are some sources of error, okay, and it's some things that we've seen before. One source of error is the gain error due to the finite gain of the op-amp, and another one is this offset voltage. Another problem with this type of super diode is that it has a saturation problem, okay, and so if you have like this negative voltage here, then at the input, then what happens is the output voltage is 0 as desired, and the voltage across the op amp is now negative, and the output V1. Okay, that's really messed up right here. Wow, I really messed up. This is I did some really bad typing this morning. Okay, so but what happened is that it saturates at the negative supply limit. I'll correct that when I put it up online. Okay, so a saturated output takes time. I really lots of poor typing. It takes time for the internal circuits to recover, slowing down the response time. Okay, so that's what happens. So remember, this is a comparator. It's going to saturate down to the negative voltage, and once it's saturated, yes, that's what you want. But the problem is that when you're trying to flip back really fast, it takes time for the internal electronics in here to adjust and get back to the next switching state. Okay, so that's if you want something to react really fast, this is not the best way to do it. There's a better way. Okay, and that's with this method right here, using 2 diodes. So this is a non-saturating precision rectifier. Okay, so to solve the saturation problem, use an inverting amplifier with a second diode to keep the feedback loop closed with the output V0. I'm doing really bad typing this morning. With the output being 0 here. Okay, so let me try to explain what's going on here. Okay, so in this case, oh yeah, and this is something I found out in the book, and you guys probably realize this too, but sometimes if they don't have anything here between nodes, you're supposed to assume that it's like an open circuit, and then sometimes you're supposed to assume that it's not an open circuit. In this case, you're supposed to assume that it's not an open circuit. There's actually something there, so I've actually inserted this here. But if you reference the book and you're reading along and you see nothing here, it's not really open circuit. They're I don't know. I guess you just have to recognize that just from reading what's happening. And the reason why I know that is because there's actually current flow passing through this resistor, right? So if this was open, you wouldn't have any current flow passing there. So for positive voltage right here, the output voltage at V1, it becomes negative, okay? And you can see that right here. So this voltage right here is 0. It's at a virtual ground, right? And so what happens is that this voltage is 0. You're having a voltage drop right here. So this voltage right here is negative of that voltage drop, okay? And so so that forward bias is this, where this voltage is 0, that's lower than 0, it's negative, so this voltage is higher, so it's forward biased. Okay, and so current, is able to pass through this diode right here. Yeah, so now another thing that's happening is that, since the inverting input is at a virtual ground right here, the current in R2 is 0, and the output out here is 0, and this is reverse biased. So remember, this is at the virtual ground, 0, because of that, right? So that's 0 volts right here. And this over here, if this is off right here, there's no current, so this is going to be 0 volts. So there's no current passing this direction, okay? And so this voltage right here is the same as this voltage right there. So that's 0 volts. So that's if it's forward biased. If this is a positive input. For the case of negative input, this diode D1, that turns on and supplies current I right here, and load current I, and this D2 is now off. Okay, and the circuit then becomes like an inverting amp with this type of gain right here. So just think of it as this part right here not even existing. This is off, no current is flowing through here, and you just have a non-inverting, an inverting op amp with just this as feedback and this as your input. Okay, and then now you do have a voltage at the output, which is negative feedback over the input times your VI coming in. Okay, now that so what that looks like, it looks like this. Okay, so same kind of shape, except it's now mirrored across your axis, right? So it's negative, but it's the type of shape of the superdiode you want without that saturation problem.
So does that not do the same thing? It's just the inverting output?
Yes, except you have this.
Okay.
That's the difference here. Yeah. Otherwise, you'll just have a ramp that just continues on through. Okay. But these things are used for when you want to have some kind of like rectifiers, something that works better than just a regular diode, where you want to get rid of that your diode voltage that turns it on. If you want to get rid of that, it's good for that. Yeah. I'm not sure exactly. Well, yeah, the book didn't talk about what happens for a large reverse bias type of current, if there's any breakdown that can occur, but at least you get this part right. Okay, so here's an example of like a AC voltmeter, and it's sort of similar to what we just seen before, except comparing the two, you can see the directions of the diodes right here compared to this right here. They're like in the other directions. And also you're going to add on this low pass filter. Okay, so what you're trying to do is make like a voltage meter. So this is a half wave rectifier circuit, which is right here. It could be combined with a low pass filter to form a basic voltmeter. And so let's say your input right here is this sinusoid with this at this frequency. Okay, at this node right here, you can expand this out in a Fourier series, and it looks sort of like this, okay, with your components. And this is a rectified sine wave that looks like this right here. That's what it looks like at V1. I mean, right here, okay. Now at the output, if you're low pass, if you have a low pass where you set your cutoff frequency to be much less than your frequency of your input, then your output can be estimated to look like this. I mean, it'll have some components, but this will be the major component, and this is what it looks like. Okay, it's pretty constant, and again, it's low pass, right? So high frequencies are filtered out. And so that's what that looks like. Okay, so that's just an example the book gave for application of this kind of stuff. Yeah. Okay. So now let's look at the Schmidt trigger. And so so now we know about these comparators, right? They were comparing the inputs right here, but one of the problems that occurs is, especially for the high-speed comparators, is if you have a very noisy signal coming in. Because if you have a noisy signal coming in, what will happen is, yeah, it'll work just fine as switching back and forth, but you don't want all that switching to happen, right? You want it to like switch, stay in this state until you have a large enough signal coming in to switch it to another state. And you don't want the noise that comes in to do your switching for you. Okay, so the idea here is to use a Schmidt trigger to handle that. And of course, that's really important for digital systems because a lot of times you only want a single transition at a time and not all these multiple transitions. Okay, so how that works, so the Schmidt trigger, it uses a comparator whose reference voltage from a voltage divider right here is its positive feedback. So here's a reference, right? Compared to what you had before, some reference. Now the reference right here has some feedback associated with it. So that means that here's your comparator, right? Its reference right here now depends on what state it's in, which is really nice. Okay, so what that means is that let's call this beta right here just R1 by voltage division, R1 divided by R1 plus R2. Okay, we're going to use that for this, where here's R1 and R1 plus R2. So if your output is positive for this comparator, it's going to saturate up to here, right? That's what this is. This is going to be your VCC, right? But what this becomes is a fraction of VCC, which is beta times VCC. Now, if you did a comparison and it fell low, then that would be at your negative VEE, right? But then this right here will be a fraction of that, so that ref would then become negative beta VEE, okay? And so this is what you get. So let's say, so here's the output right here. Here's the input, okay? So let's say it's at this state. And so you're at this voltage right here. If you're having some noise over here, you know it's not going to flip. Okay, so you're having some noise. Now, if you increase the voltage that's to go beyond the noise, you have to get the voltage up to this value right here for it to switch to negative VEE, right? Because if you're at this voltage right here for input, right here, if that's your input, your output is still VCC. If you're over here at input, your output is still VCC. Okay? Your input has to increase all the way to beta VCC in order for it to finally switch to this state, VEE. And then any higher voltage will still saturate to right here. Now, if you're in this state over here, and that's your input, you're still at negative VEE. Now, in order to switch back, you have to decrease your voltage past 0 all the way down here to negative beta VEE to switch back up to this state of VCC. So, so what's happening is that you have this margin of error between here and here, which is like this hysteresis, right? So your input is going at several values along here, right? But it has to go up to here to finally switch down here for the output. And then if you're over here, then your input has to go way back over here to switch to this state. And so your noise is typically, going back and forth right here, and that's not enough to get you to those states to switch. Okay, so that's one of the benefits of a Schmitt trigger, is to avoid that type of noise for your input comparators. Okay. All right, so any questions about the Schmitt trigger? All right, great. So well, that's all I have for today. And so I guess we're gonna get out of here 10 minutes early. All right, so have a great break, and I'll see you guys back on Monday.